We're going to learn today how to write another form of electron notations. And this is a shorter version. We call this one just electron configuration notation. Most of the time we shorten that to electron configuration. Not that that's short either. So the difference in this and orbital notation is that in electron configuration, we don't show the orbitals. We don't draw the individual orbitals out. So really, with electron configuration, what we need to think of is, for SPs, Ds, and Fs, is the maximum number of electrons. So in other words, if I'm looking at an S sublevel, which has one orbital, each orbital can hold 2 electrons. So an S can hold a maximum of 2 electrons. A P sublevel, which has, remember, 3 orbitals, 3 orbitals times 2 electrons each, that gives us 6 electrons. A D sublevel with its 5 orbitals can hold a maximum of 10 electrons, and an F sublevel with 7 orbitals can hold a maximum of 14 electrons. So more so than the number of orbitals in each sublevel, we are going to concentrate on how many electrons we can put in each sublevel. And so let's start with aluminum. So if we go to the periodic table and find aluminum, we're going to see that aluminum's atomic number is 13. Neutral atoms, the number of electrons and protons are equal, so aluminum has 13 electrons. Now, when we do our electron configuration, we're going to start the same way. We still have to follow the Aufbau principle, that electrons will fill from lowest energy to highest energy. So we're still going to have to follow this order. So we're going to start with 1s. We're going to write that down, but this time, instead of drawing that orbital and the arrows for the electrons, all that we have to do is put how many electrons are in this sublevel with a superscript. And so I can put 2 electrons in this S sublevel. That means 2 electrons. So a 1s sublevel with 2 electrons in it. That's full. So I move on to the next one, which is 2s. I write that down, 2s. And again, I'm just going to put how many electrons can go in that sublevel. And so an S sublevel with its 1 orbital can only hold 2 electrons. There we go. After 2s is full, go to your next diagonal and we're at 2p. So I'm going to write that down, 2p. P sublevels with their 3 orbitals can hold 6 electrons. And so I can put up to 6 in that 2p sublevel. That gives me a total of 10 electrons, right? 2 plus 2 plus 6 is 10. I need 13, so keep going. After 2p is 3s. And so 3s, S sublevels with 1 orbital, 2 electrons. Now I have 2 plus 2 plus 6 plus 2, so that is 12 electrons. I need 1 more to make my 13. So after 3s comes 3p, and I can put I could put up to 6 electrons, but I only need 1 more. So that is aluminum's electron configuration or electron configuration notation. So we're showing electrons, how many electrons, instead of showing each individual orbital. Now, if we think about quantum numbers here, we really can't assign all 4 quantum numbers to any particular electron because we're not showing individual electrons. Now, I could say, like if I'm looking at this 2p sublevel, I know that all electrons in that sublevel, n is equal to 2 and L is equal to 1. Because 2, that's my principal quantum number, P, my sublevel, has an L value of 1. So those are really the only two quantum numbers that I know for sure about these 6 electrons. And since I don't show any more information than that, I can't assign the rest of the quantum numbers to any particular electron. Okay, well, let's do another example of electron configuration notation. And so we will try let's do germanium Ge, whose atomic number is 32. So 32 electrons. And we need to remember that this off-bow, however you want to say it, principle still applies. So we're going to start with 1s. S sublevels, 1 orbital, can hold 2 electrons. Then we're going to go to 2s. S sublevel, 1 orbital, so 2 electrons. Then 2p. How do I know I go to 2p next? Because I'm following the order as I go along these diagonal lines. And so 2p with its 3 sublevels can have 6 electrons. Then 3s. S can hold 2 electrons. Then 3p can hold 6 electrons. Because it's a p, it has 3 orbitals, times 2 electrons in each orbital gives us that 6. And then what comes after 3p? This is where some of us mess up if we're not following the diagram. So we end up at 4s. So 4s is next, and s sublevels with 1 orbital can hold 2 electrons. After 4s, we go to 3d, and a d sublevel has 5 orbitals, 2 electrons each, gives us 10 electrons. Now, we need to know how many electrons we've used. 2 and 2 and 6, there's 10. 2, 6, and 2 is another 10, that's 20, and this 10 makes 30. So I just need 2 more. So what comes after this 3D? 4p. So 4p, I only need 2 more electrons. So even though I could put up to 6 electrons here, I only need 2 more to give me my 32. And so that is the electron configuration of germanium. If you have any questions or need any help or more examples, make sure that you let me know.